Scientific measurement. So let's say that you wear a watch that measures time with a precision of 1 second. So this level of precision would come in handy if we were timing a very close race. But if we just needed to know what time it is, we wouldn't need to know the seconds. Less precision would be okay in that situation. Now let's say that you forget to fall back an hour during daylight savings time. So the time on your watch is still going to be very precise. It still measures to the seconds, but it won't be very accurate because it will be off by an hour. So what I'd like you to do is to look at these images here to help you think about what the difference between accuracy and precision is. So you can go ahead and pause this video and come up with a definition for these terms. So the definition that I have for accuracy is how close those measurements are to the correct value. So if we look at the first dartboard here, we have both accuracy and precision. So accuracy is going to mean hitting the bullseye in this metaphor here. Precision is related to how close together each measurement is. So if we look at this middle board here, we have poor accuracy because we are nowhere near the target, but we still have good precision because all of these measurements, all of these darts are in the same place. So a chemistry student finds a piece of gum to contain 3.2 grams of sugar. According to the nutrition facts, the gum has 4 grams of sugar. So there is error associated with any measurement. And one of the ways that we can express error is through percent error. So first, this equation has a couple different values here. We have the experimental value. This is going to be what the students or what you get from your actual experiment. The accepted value then is what it really is, the bullseye, the correct answer. So another thing that I want to point out is that this has these absolute value lines. So this means take whatever that is and make it positive. So your experimental minus accepted, even if you get a negative number, just change it into a positive number because your percent error should never be negative. So think of it this way. Let's think that we had a test and we got a 16 out of 20 on the test. Well, that would be an 80%. So then our percent error there would be 20%. Those are the questions that we got wrong, 4 out of 20. So same idea here. So I'd like you to take a moment to pause this video and go ahead and try to solve for the percent error for this question. So to solve for percent error, we need to take our experimental value minus our accepted value. Remember that these absolute value lines are going to make that difference a positive number. So you're not going to have negative 0.8 here. You're going to have positive 0.8. So then when you divide by the accepted value, that's going to give you some fraction. And then if you multiply by 100%, we get 20% here. So there is error associated with any measurement. So one of the ways that we can express the accuracy of our measurements is to give a percent error. A low percent error means a high degree of accuracy. So here on the screen, we have a door, and we're trying to measure the width of this door. And we have these 3 different rulers here. So my first measurement here, I know that the ones place is a 0 because it's less than 1 meter. This particular ruler, I'm going to call that ruler A, is not very precise. It only goes from 0 to 1 meter and there's no tick marks in between. So I know that the ones place is a 0, and I guessed that first decimal. Now, when we look at the next ruler, I'm going to call this guy ruler B. Ruler B has more tick marks. So my measurement for this one is going to be a little bit more precise. So I am certain that this is still a 0. I am now certain that this is a 7 because I have a tick mark for 0.7. And then I estimate this last place. So I can't estimate another decimal place because I wasn't even sure about that 8. So I can't guess any more decimals unless I get more tick marks. So this bottom ruler, we'll call that ruler C, has more tick marks. So now I'm certain of the 0, I'm certain of this 7 and this 7, and I guessed the 1 here. So when you measure something, it's the places you know from the tick marks, and then you guess one place smaller. So each of these rulers is different because they have different amounts of tick marks. So the bottom ruler can measure out to more decimal places than the top ruler. And this is because there's more tick marks. So we always guess one place smaller than what the tick marks provide. And then which ruler gives us the most precision? That's going to be the bottom ruler. We call that ruler C because it has the most tick marks, the most increments. In question 7, we have several graduated cylinders that we want to properly measure the volume of liquid inside. So one important thing to remember is that if you have water in a skinny tube, water is polar and glass is also polar. So it kind of draws the water up the edges there and it creates this curve, which we call a meniscus. So whenever we measure volume with a graduated cylinder, we want to measure the bottom of the curve, the bottom of the meniscus. So let's start by looking at this first one here. So first we want to figure out what it goes by, what the increments are on this graduated cylinder. So this mark is 20 and this mark is 30. So this must be 21, 22, 23, etc. So this goes by 1. So we know the ones place for this measurement. So if I wanted to measure this meniscus here, this curve, I see that that's resting exactly on 35. So I am certain of the 3 and I am certain of the 5 because I have increments for that. So I would need to estimate my next digit. Now to me, it looks like it is exactly on 35. So I would need to put 35.0. If you thought it was just under that, you would put 34.9. If you thought it was just over that, you would put 35.1. So the units on all of these would be milliliters. Okay, let's look at the next one. So once again, we got to figure out what it goes by, what the increments are. So this is 6 and this is 7. So this must be 6.1, 6.2, 6.3. So this goes by 0.1. Do you see how that's a smaller number than we got for the previous graduated cylinder? So what this means is that we always know the first decimal from the tick marks. So we would have to guess the second decimal place or the hundredths place. So this to me looks like it's exactly on 6.4. So I would need to write 6.40. If you think it's just under, or if you think it's just over, all of these measurements would be correct for this graduated cylinder. Now, the reason you can't just write 6.4, the reason that doesn't work here. So if I wrote 6.4, that would be telling me that I guessed the 4 and I knew the 6. Well, that would be this type of graduated cylinder. So if you told me 6.4, I would know that you were using a less precise graduated cylinder. So when we're talking about precision here, if you notice, all of these numbers here are different by plus or minus 0.1. In my next graduated cylinder, these numbers are different by plus or minus 0.01. So these measurements are very close together because this is a more precise graduated cylinder. So go ahead and take a couple of minutes to pause this video and try the next 3 graduated cylinders, and you can come back here when you are ready to check your work. So the next graduated cylinder here, this is 30 and this is 40. So this first mark must be 31, 32, 33, etc. So it goes by 1. So I know the ones place from the tick marks, the measurements on the graduated cylinder. So I know that my tens place is a 3 and my ones place is a 6. Now it looks to me like the bottom of the curve is right in between 36 and 37. So I'm going to say 36.5. If you had something a little bit different, like you had 36.4 if you thought it was a little lower, or maybe you had 36.6, all of those answers would be correct, and the precision on this guy would be plus or minus 0.1 milliliters. The next graduated cylinder, first we got to figure out what it goes by. So if this is 1 and this is 2, that means this one is 1.1, 1.2, 1.3. So this one goes by 0.1. So this means that I will know the first decimal from the tick marks. So I will guess the second decimal. So this looks like 1.567. And to me, it looks like it's just a little bit above the 7, so I'm going to put a 2 there. But something like this would be fine. Something like this would be fine. All of those answers would be correct there. Okay, the last one here. This one is a little bit tricky. So let's think about what it goes by first. So if this is 100 and this is 200, each of these tick marks must be 10. So this is 100, 110, 20, 30, 40, 150. So this goes by 10. So this means that I will know the 100 and the tens place. I'm going to guess the ones place. So to me, this looks like 294 or maybe 295, something like that, milliliters. So we know the 2 from the tick marks. We know the 9 from the tick marks. And then that last digit, the ones place, is what I'm guessing here. So I'm guessing 4 or 5. So how can there be more than one right answer? Remember that there is error associated with any measurement. That error could be human, or it could be instrumental from the tool that you are using. We also have a certain level of precision with each measurement. So if we are within the precision of the instrument, that measurement is still going to be correct. So you have journal write 1 here. You want to explain how 10 milliliter, 10 with a decimal milliliter, and 10.0 milliliters are different measurements. What precision did the graduated cylinder have? So I'm really asking you here, what does it go by? what were the tick marks on the graduated cylinder here that would give us these precisions here in our answers. So this is telling you, this 10 with the decimal, this is telling you that this is a 0. We estimated that 0. This one is telling us that we estimated the 1. And this one is telling us that we estimated the first decimal place.